Okay, so I think the recording started at the same time I was sharing my screen, so let me reshare. That sometimes causes it to freeze. All right, do you guys see my screen? Just give me a quick thumbs up if you see it.
Yeah, I think we can see your screen.
Great. Okay, so I'll talk about one of the products I'm very passionate about is turning video calls into health sensors. And so the problem that we're trying to solve is this. Today, if you go to the clinic just for some basic triaging, there's this idea that you need to get your vital signs measured. So many of us have gone to the UCLA hospital or UCLA Health for regular checkup. And what do they do? Well, the first thing is you walk in and maybe a nurse takes your vital signs, your blood pressure, your heart rate, your temperature, right? And then you wait 15 more minutes in the room while they look at that data and log that data, and then maybe a physician comes and sees you. So many of these visits are for the purpose of these elementary filling out a questionnaire or for getting these elementary vital signs. So by some measure, these visits are conducted solely for the purpose of getting these vital signs and being triaged, okay? So that leads to a large line at the hospital where people are just visiting the hospital to get triaged and get their vitals recorded. And so what we want to do is we want to avoid that. What if you could get your vital signs measured while you're at home? In fact, what if you could get your vital signs measured while you're on this video call? And that's our goal. So imagine I could get the heartbeat, for example, of everybody on this call right now. I could probably tell who is nervous about their midterm, or if you guys have access to my heartbeat, you can tell when I'm lying, right? So how do we make that happen? And the solution here is to turn video calls into health monitors, which basically means we're going to create these algorithms that enable cameras to see the skin and extract meaningful slight variations that are invisible to the human eye, but visible to machine algorithms. If we can do this successfully, it's going to be contact-free, reducing infection, not only in a pandemic, but even in flu season that exists. 4 billion people on Earth have a smartphone, so it could be widely deployed. And when we do end up measuring vital signs and we do flag something that is concerning, then we have a stronger prior to triage them to the hospital to get them here right away. We can prioritize their care and therefore deliver even better care to a wide variety of patients. The technical blocker here is to image the invisible from video. Vital signs can ordinarily not be seen through skin, and particularly dark skin. So what our goal is to essentially take these pictures of a person and look at those slight color variations in the blood flow that are occurring in some oscillation. So we look at these slight variations in blood flow, and from these slight variations, we can extract things like, for example, the heart rate. Now, the problem is it doesn't work on dark skin. Just like, we all have friends that at a party, if they have light skin, you'll see their, like after they have probably shouldn't say this on a recording, but let's say they've had kind of a few beverages, then you can see that they have a glow, right? They have a blush to them because you can see the blood variations through their skin. In contrast, if they have dark skin, I don't know how many times you've seen one of your dark skin friends blush. Probably never, depending on how dark their skin is. So this becomes a really hard problem when you have dark skin. And it's one that I and along with some really wonderful collaborators, in particular, I'd like to highlight Krish Kabra and Pradyumna Chari, who are graduate students at UCLA Engineering, as well as physician collaborators. And what we're trying to do is we're trying to scale this to real-world patients. This is what it looks like. Okay, this is a subject. A gentleman is sitting in front of a cell phone. So you can see that there's a zoom in of a cell phone that is taking a video of the subject. The subject is hooked up to the health monitor. Okay, so it's hooked up with a pulse oximeter, blood pressure cuff, and all these types of leads, and you're getting a signal on this, this monitor. And so this is the top figure here is the heartbeat from the pulse oximeter and the monitor. So it's about 55 beats per minute. Now, what we've done is this is actually a video that's happening right here. This image is actually really a video. You just can't see any variation. So it's a very short duration video. But if you look at this video and you magnify the variations, right, almost like taking the Fourier transform and magnifying it, then what you see is you see these color variations and head motion. You can see there's a slight head motion that's happening in the magnification. And if you do that and you correlate these color and motion variations, you can actually get a predicted heartbeat on the right-hand side purely through the video. Okay, so this is a heartbeat signal that's happening through the video. And you're getting about 57 beats per minute. The device used here was a Samsung Galaxy S10 phone. So there's no modification that's being made to the hardware. It's just a Galaxy S10 taking a video of a person and getting their heartbeat from that video. Now, the way it works is it works through a computer vision pipeline, and I'm happy to talk offline about computer vision, and we'll do a little bit session about computer vision. But basically what we do is we first break the problem down. We, like Julius Caesar, Roman Empire, right, said divide and conquer. So we want to divide and conquer here. First, what we do is we actually remove portions of the face which give us artificial signal. So these include the eyes and these include the lips, right? Person's mouth movements could be confused in the video when you encode a feature map as being somehow correlated towards the heart rate. So remove the eyes and the lips, and that's why they're blacked out. And then we essentially create a signal to noise map, and we weight the color channels, and then we extract some sort of harmonic analysis. This could be a wavelet transform, it could be also a Fourier transform. And from this, we're able to extract a heart rate of 59 beats per minute. So, what does this impact immediately? Well, in the short term, this device is able to, with the Galaxy S10, diagnose tachycardia. Tachycardia is a fancy name for basically heartbeat that is going really fast, right? Above 100 beats per minute. So we can also diagnose the beat-to-beat regularity. You see in this patient right here, the beat-to-beat is very regular, meaning that each beat is kind of periodic. But in general, the beats could be kind of uneven, and that's a sign of atrial fibrillation. So beat-to-beat irregularities can also indicate stroke, medication reactions, and much, much more. And although they're present on kind of a small minority of subjects, when you do detect that, that is a cause for concern. So this is just the tip of the iceberg, right? There's this huge kind of ecosystem for invention that surrounds this intellectual property, right? Of how we sense vitals, how we create a data platform for it, and then also how we commercialize it. I apologize for kind of including a business-oriented slide in this. This is a carryover from a pitch at the medical school, but there are these different pathways towards scaling this to something bigger. Okay, so that is just a quick snapshot of some of the research that my group does on computer vision related to healthcare. Any questions at this point?
I have a question. Why is it that you take out the eyes and the lips? Is it just for privacy?
No, it's actually not for, it has the benefit of privacy, but it's actually not really for privacy. It's really so that the eyes and the lips actually start to interfere with the video signal, right? Because what you're doing is you're taking these pixels, and each individual pixel is not giving you much signal about the heartbeat, but you're aggregating all the pixels together. And if you aggregate pixels from your lips and your eyes have a different kind of motion pattern that's due to your eye movements, right? Microsaccadian and so on. So that's not indicative of heart rate. The eye is an independent sensor that behaves separately from the heart. Similarly, the lips themselves, they could have some correlation to if you're talking or your speech. So you want this device to work if somebody's speaking as well, and it does.
Okay, thanks.
Hey, I have a quick question. Really cool work. How do lighting variations affect the performance? For example, maybe from the external lighting, or I know a lot of modern smartphones have auto HDR. Does that affect performance at all?
Yeah, so lighting variations do affect the performance. in general, part of the algorithmic novelty is to come up with a lighting invariant way to do this. And to do that, we do some photometric texture analysis and lighting rejection. So there are ways in computer vision to create invariants to lighting. And so if we don't apply these invariance techniques, then yes, lighting corrupts it. But there are ways to scale it so that lighting does work.
Awesome, thank you.
I have a question. What were some of the main challenges with this project?
So I think the main challenges, the main challenge to me with these kind of translational projects is getting access to subjects to test on. And we actually had a big challenge in our group where we were not actually able to find enough subjects across the skin tone spectrum. So to call a spade, right? We don't have that much Black representation in our department, right? Which is definitely a separate issue, but I won't go into that here. But where it actually starts to impact the science is when you can't have volunteers of this type, and testing your device on a more diverse population. So I would say getting the subjects was the hardest part. The algorithm itself, because we do kind of computer vision in our lab, my students, Pradyumna and Krish, as well as myself, we're kind of familiar with computer vision techniques, and we can kind of own that part of the pipeline and kind of set our schedule that way, right, to optimize the vision algorithm. But if we don't get patients on a regular cadence coming into to do the test, especially since we're doing this during COVID-19, then there's no data for us to actually look at and process.
I see. Thank you.
I have a question with regards to the test subjects that you had and the algorithm itself. So were you did you also change some parameters based on the subject's skin color, or the algorithm auto detects those features?
We have two modes. I think one mode is automatic, auto detect, and then we have a second mode that does a two-stage approach. It estimates the skin tone, which is kind of easy to do from recognition algorithms, and then proposes a correction factor.
Thank you.
Okay, so we also have Chinmay, it looks like here. So it's another very exciting project from our group on taking video and discovering the laws of physics from video. So I can show that slide, but I would rather use this time to kind of learn more about you all on the call, and then kind of see how to tailor the discussion of computer vision. So I know Cody, you're undergraduate. Many of you are graduate students. I see Zenkui and Chinmay and many others, Glenn and many others, are Alejandro, are graduate students. So kind of raise your hand if you're new to computer vision. Okay. All right, so particularly undergraduates. Great. Terrific. Okay, so what we're gonna do is I'm gonna fire up the tablet here, and we'll do like a little bit of a brief 10 or 20-minute lecture on what computer vision is and what the key things you should know are. Think of it like a cliff notes for computer vision. So maybe it'll hopefully excite you to take a class in it. And before I do that, I'm gonna play a video from Elon Musk. And I think he really puts the vision problem in some nice context. Okay. So I'm going to share my screen, and hopefully the video will share as well. Okay, do you guys see my screen?
Yeah.
Awesome. So let me pass through some of the audio. Just give me a quick thumbs up if the audio is playing.
No, I don't think.
Let me reshare it. I'll blow this up full screen. Okay, share sound. Got it. All right, so we'll try part 2. Just speak up if you can hear the video.
It's got autopilot. And you put out this video a while back, 3. So it's supposed to be coming in July-ish.
Yeah, it's looking quite good for starting production in July, yeah.
Wow. One of the things that people are so excited about is the fact that it's got autopilot. And you put out this video a while back showing what that technology looked like, or would look like.
Yeah.
There's obviously autopilot in Model S right now.
Yeah.
What are we seeing here?
Yeah, so this is using only cameras and a GPS. So there's no LiDAR or radar being used here. This is just using passive optical, which is essentially what a person uses. The whole road system is meant to be navigated with passive optical or cameras. And so once you solve cameras or vision, then autonomy is solved. If you don't solve vision, it's not solved. So that's why our focus is so heavily on having a vision neural net that's very effective for road conditions.
Right, many other people are going the LiDAR route. You want cameras plus radar is most of it.
You can absolutely be superhuman with just cameras. Like you could probably do 10 times better than humans with just cameras.
So the new cars being sold right now have eight cameras in them. That they can't yet do what that showed. When will they be able to?
I think we're still on track for being able to go cross-country from LA to New York by the end of the year, fully autonomous.
Okay, so a car, by the end of the year, you're...
Okay, so that was just a short snippet from one of Elon Musk's talks. And there's a lot of, there's certainly an interesting reception in the vision community to Elon Musk and kind of his projections of when autonomy will happen. But I think one thing that I really took away from that clip was if you don't solve the vision problem, then autonomy is not solved, right? You can't have a blind driver ordinarily. Okay. So what I'd like to do is I'd like to talk about a little bit about the field of computer vision, and I'd like to condense that into 10 minutes or so on the tablet, if that would interest people. Okay, so I think this would be a better use of time than talking about the research in my group, because hopefully this motivates you to do research with me or take classes. But I think it's better to understand the field as a whole. Okay. All right, so let me share my screen here. So you should see a iPad screen. Okay. Good. Okay. So vision, right? Computer vision. The goal of computer vision is to teach machines how to see. For those of you who have not taken any of my classes, do you guys know when computer vision started? Any guesses as the field?
Wasn't it something like it was in 1980? An MIT grad student was given a very simple problem of getting a computer to like detect a cat, and it turned out to be a much harder problem.
Yeah, so close. The date is a little off, but yes, exactly. So at MIT in the 1950s, the perceptron had come out, right? The perceptron neural network, and the pioneers of that, Marvin Minsky, Seymour Papert, and others said, you know what, they were faculty at MIT, and they said, okay, you know what, let's hire an undergraduate for the summer to go work on using this for imaging. Okay, we'll just have a neural net connected to a camera, and the computer will tell us what the camera sees. Okay, so 1950s, undergrad, summer project. describe what it sees. Okay, so this was the 1950s, and clearly it was not done that summer. In fact, they realized at the end of the summer that this is a big problem. We have this image, which is a bunch of pixels, like a whole bunch of pixels, but it's completely unstructured data. You have a cat that looks like a cat in one photo, and I can show you photos where a muffin looks like a cat, okay? If you take the picture at the right angle. And there's no ordering to it. A cat can, it's not like the cat is going to be in pixel 3,2. The cat can be anywhere in the image. The cat can be of different sizes, different shapes, different characteristics, right? But somehow our human visual system recognizes it as a cat, but it's not possible to include a rule for a computer to go and rule-based recognize this as a cat. And so in the 1950s, they basically said, you know what, let us give up on this problem. Now, progress in vision essentially stopped at this point. There wasn't really much to do because you couldn't really do anything. So a lot of smart people said, you know what, let's work on computers and let's work on making silicon better, and we'll worry about vision later. So today, of course, we can tell cats from dogs with superhuman accuracy, but this has only been powered in the last 5 years. Okay, so historically what happened in the 50s, so there's been a dead period. Then in the 1980s, a small contingent of people, academics primarily, with no industry affiliation, they kind of got together and said, you know what, let's go back to Minsky's problem from the 50s at MIT, and let's kind of systematically understand how a computer describes what it sees. So in the 1980s, they took what's called a low-level vision approach. They said, you know what, the image that we have is made up of these primitives, right? These primitives are, for example, textures like edges and corners and things like that. And these are the building blocks of an image. And they were right, and they came up with this theory of how you could represent an image using low-level primitives. So we call this the first R of computer vision, which is representation. So there wasn't really much you could do with representation in the 80s. You could, for example, compress an image, and that's kind of great, but you couldn't really analyze anything about an image. You couldn't recognize it because the edges and corners would shift from, kind of cat to dog, and there would be too much variability even in the edges and corners. So in the 1990s, fast forward kind of a decade, you start to have this representation of kind of patches or mid-level vision, where you kind of have descriptors that kind of describe correlating points in the image. You can match one pixel to another pixel. So you're adding some structure to the image representation. So we call this structured representations. To reconstruct an image. So we essentially have now the structure that applies to an image, and that enables us to reconstruct what the image looks like. We call this the second R, which is reconstruction. So at this point, we start to see, this takes us to around, by the time it's completed, let's call this 2000, which is kind of when it sort of completed. By the time we were hit the year 2000, now what we could do is we could take cameras and we can build a 3D model of the world. We can't tell you what is a cat and a dog, but we can tell you like the spatial position of points in the world. And this started to become immediately impactful for robotics. So we start to see kind of an application, killer app. Robotics. Okay. So in the 2000s, robotics really took off with vision-guided robots. Those of you who did high school robotics, being kind of fairly young, you guys would have been probably exposed to some computer vision in your high school robotics, which would largely be reconstruction-based vision. We're trying to reconstruct some model of your world. So this really catalyzed that field. I think this really injected a shot of life into the field of robotics. And it was powered by how we can now reconstruct the image. But even if we can reconstruct the image, even if I can tell you the three-dimensional position of objects, it's still a pixel representation. I'm still telling you like a pixel in X, Y, Z. I'm not telling you which pixel is part of a cat and which pixel is not part of a cat, okay? So it took until about 2015, I would say, is the year. In 2015, so fairly recent, we finally hit the third R, which was human level recognition. Okay, this is the third R vision. And there was an article in Forbes yesterday, and that article in Forbes 2021, which would be yesterday, right, in year 2021, was talking about how computer vision is going to create the next $1 billion of startups, right? The most $1 billion startups, because once you hit this is in research, we hit it in 2015. So outside of research, this is now making its way to product. And recognition is the key, right? Because now I can tell you, I can look at a medical scan, I can tell you, oh, this is a tumor. This is not a tumor. And I can make a medical decision based on that. I can recognize the heartbeat from the video. I can recognize what that is. Okay. I can recognize, for Elon Musk's problem that he's talking about, fundamentally, he wants to understand where each pixel belongs. Because from the second R, he knows where each pixel is. He knows the XYZ position, arguably, of each pixel. Okay. So if he can know what the XYZ position is and come up with a label that this is a road, this is a pedestrian, this is a building, he knows where to drive and where not to drive. Okay. So once you hit the third R, you have essentially, solved a sufficiently large chunk of the vision problem. Okay. And that's what we hit in 2015. So now in 2015, what we hit was the third R, and we hit that for image classification. Just to be clear, we got classification rates. If you give a data set of, let's not just say cats and dogs, but let's say I give you like a general, let me come up with like 1,000 objects that are common in the world. Cats, dogs, airplanes, trains, cars, bicycle, and so on, right? Come up with these 1,000 examples, and I can come up with an image classification challenge. And I can give you these 1,000 examples and ask you to label which one, as a human, I can give you a bunch of pictures. And we've all done the CAPTCHA code, right? When we're logging into our computer, we ask you to recognize. And the error rate that a human has is about 5%. That's the human. The human actually may have trouble recognizing cats from dogs in some cases, and that's why it's 5% error. Now, throughout this decade, the machines were at like 90% error here. Maybe they were at 50% error here. So they're basically taking almost a random guess if you have a binary category. But in 2015, you got down to 3.5%. Okay. So now you're actually doing better than the humans who labeled the data set. And that was an inflection point. So now that the vision system is better than the human, it's going to change a whole bunch of industries. Doctors, it might be criminal in the future to not use a machine to aid in radiology, right? Because the machine can actually have an error rate that is almost twice as good as a human. Autonomous driving, that's another example. Virtual and augmented reality. Okay, so that's kind of what we hit in 2015, but we only hit that for image classification. We only hit it for image classification. So there are harder problems in vision. There are 4 fundamental problems in vision. And that's where we are today. So we're 2021. Okay, so there's 4 fundamental problems. The techniques are the 3 R's, but there's 4 open problems. There's 4 problems, actually 3 are open, 1 is solved. Image classification. This one is a solved problem as of 2015. Any guesses on another one in computer vision?
Segmentation.
Segmentation, that's right. So segmentation. And you can have kind of, typically you might have also instant segmentation. That's the third problem. And then the fourth is object recognition, object detection. Okay. Now I'll just order this by difficulty. So the easiest one is image classification. The next easiest is object detection. Next easiest is semantic segmentation, or just segmentation. And the hardest is instant segmentation. So these are the four problems that are on nearby horizon. These are the four core problems that are facing industry. And you have additional problems in the future, like activity recognition, emotion recognition, etc. Right? How do you teach a machine to start to reason about the emotions of people? For example, if I see a woman hugging a small boy, I might think about, right, how that could be, for example, a woman hugging her child, right? And see that there's an emotion associated with that. Activity, if I see somebody lifting weights, that's different than somebody lifting a box for work versus lifting weights for recreation and exercise. Okay. All right, so these are your four problems in computer vision that we're looking at right now. If you take a more industrial mindset, and if you take a more academic mindset, these are the problems kind of really on the large scale horizon that primarily interest academia. Okay. So this is a brief snapshot of computer vision, and I'll kind of open it up for discussion here.
You might know this, but I'm not sure if we can see you right now.
Yeah, I think for some reason my camera is not working with Zoom. So let me just quickly leave the meeting and rejoin.
Okay.
Okay, so short of doing a computer restart, I don't think I'll be able to get a camera up and working. So you'll have to use your imagination.
Sounds good.
So I'd like to see if there are any questions here that I can answer.
Yeah, I actually have a question. What is segmentation exactly?
Oh, great question. So actually, since I don't have video, let me substitute by using the tablet again. That might be better than talking to, literally, it looks like a black screen. Okay, so So segmentation is like this. You have an image, right? What is an image? An image is just a matrix of pixel values that could take any form, right? It's very, very unstructured data. And so let's say I have pixel values, like let's say I'll draw a 2x2 grid just for the pixel values. That's something like 170 and 83. And so you could have kind of like this bright object, and it's surrounded by something pretty dim, like okay, let me draw. Just to make it very concrete, I'll draw a 4x4 grid. Okay. Okay. So you might have some sort of bright object in the middle, like an image value ranges from 0 to 255. And so you might have something like 220, 210, 215, 210. And then outside of that, you could have 0, 3, 7, 8, 12, 17, 18, 20, 36, 40, 20, and 10. Okay, so you can see that in the values, there's a clear boundary here between these high values in the center. Maybe you're taking a picture of a star, and the star is the center of your image frame. Okay. Now, this segmentation problem is assigning a label of 1 or 0. So this is your image I. You want to create a new image M in 0 or 1 with the size of 16. Okay. And it's going to be the same thing. It's going to be, I want to create essentially a grid of the same dimension that has 1, 1, 1, 1, 0, 0, 0, 0, 0, 0. So this is the segmentation problem because it allows you to recognize where the object is. It tells you that the object is in the center with the ones. So if a surgeon, for example, let's say this was a tumor, the center of the image was a tumor, the surgeon could take a scalpel and very carefully cut out these pixels on the image, okay, or take some action there. Or if you're doing autonomous driving, you know where the pixels are in space. With the camera, you take your camera, you have pixels, you know where the pixels are in space.
Okay, I see. Thank you.
So do you need some kind of prior knowledge that like the ones, like the higher valued numbers correspond to the image rather than the lower valued numbers?
Yeah, so you need some sort of prior knowledge. And to do that, we train machine learning and artificial intelligence data sets, right, algorithms, to extract that information automatically. So in this particular case, we might take a whole bunch of pictures of tumors, and then we realize the tumors are on average brighter. Now, there's two ways we can do this. As a human being, we can just hard code a threshold. We can say, oh, okay, anything above 150 is a tumor. That's what we could do here, right? But the problem with that is that in the real world, lighting and context cues, like if I change the lighting, this mapping might change a little bit, right? So there's no one size fits all threshold to make this happen, especially for subtle things like radiology. In radiology, you pay doctors, right, to essentially go through years and years of training so that they can recognize subtle features in an image that humans cannot recognize, like regular humans can't recognize. So you have these radiologists who are trained to spot these slight defects. And for those problems, it's very difficult to put any threshold on it.
Cool, thank you.
Quick question about, you said that we've split these problems into academic and industry. So are you saying that the 4 problems that you talked about are solved academic problems, or they just are prevalent to industry?
I think both industry and academia, maybe I didn't explain it clearly enough, but industry and academia, there's a bit of overlap on the topics, and they're both all working on these 3 topics. I would say that these 3 topics, in my personal taste, they're actually being done better by industry right now, because industry has more motivation to solve them, because it ties in with like autonomous, like one research lab at UCLA is not going to potentially solve autonomous driving in the same way that an entire division at Uber or Waymo or similar will solve it. So I would say that these problems are being studied in better ways in industry. Because why? Because it fundamentally relies on how good your AI model is. And the goodness of your AI model is largely based on the data set that you have access to. And industry has, yeah, go ahead.
Sorry, go ahead. Okay. So by AI model, I assume you mean like neural networks?
For example, neural network, yes.
Okay. Are there other sorts of machine learning models that are more often used for computer vision tasks?
So, I mean, neural networks themselves, there's a lot of variation into a neural network itself. There's different types of neural networks and very different goals for different design strategies. But not really. There isn't that much that is used industrially in machine learning outside of neural networks. People used to use SVMs as of recent years, but that has been superseded by neural networks for image tasks.
Got it.
I mean, there's still kind of, this is for performance that I'm talking about. There's still academic interest in coming up with Bayesian methods, causal models, or things like that for some of these tasks. Like the segmentation, for example, you can pose it as a maximum likelihood problem. And that allows you to then go and have nice theoretical guarantees, and you can characterize distributions like mixture models, and it'll give you some interpretability. But in terms of sheer performance, it would be neural networks would be my take on it.
So with modern GPU acceleration, do you see like image processing as being a problem for doing any of these tasks, or do you see, with the rate that GPUs are getting better, do you see that as not a problem at all?
I think it's going to be a bottleneck. Many of the images that we process are low resolution, and you can see that with like object detectors, right? The speed up, like if you had a poorly designed object detector, as researchers did, remember the state-of-the-art researchers, the best researchers in the world, had come up with an object detector that 3 years later was 1,000 times slower, right? So choosing the wrong algorithm can really lead to speed bottlenecks. And we don't know what is right and wrong, right? Because as of let me just make up a year here, let's say 2013 or so, people were building object detectors that would take about 60 seconds a frame, right? And that was the fastest that you could think of, highest performing. The next year, they came down with a different algorithm and got it down to, I don't know, something like, 5 seconds per frame, right? Something like that. So the algorithm jumps are significant, and we don't know which algorithms are designed suboptimally and which are not, right? Because this is research. So we don't know which algorithms need to be speeded up right now. So I would say that, yes, it's a combination of hardware as well as algorithm design.
I have a quick question about segmentation.
Yeah.
So I was wondering how segmentation compares to just simply using like some type of Fourier transform method to like just do the trick.
So segmentation is a problem of labeling every pixel with a class label. A Fourier transform is a little bit of a different approach, right? So you can use Fourier techniques potentially to solve your segmentation problem. And that's how they used to do it back in the day before deep learning. But the segmentation problem is very specific. It is, have a grid of pixels, give me a label of 1 or 0, which object it belongs to, foreground and background. Tell me which pixel is foreground, tell me which pixel is background. Now, of course, you have more difficult problems. You have like multi-class segmentation, where you can have 100 different classes or even 1,000 different classes that an object can belong to.
So would an example be like when you open your iPhone, like the iPhone detects your face, and like would that be a segmentation problem?
No, that would not really be a segmentation problem. That would be largely, in this particular framework, would be an image classification problem. I'm trying to classify the picture as belonging to Cody's face. So it's like a fine-grained classification problem. So this is another term that, so even though classification is solved, there's also something called in research called fine-grained classification, which is not solved, right? How do I tell, for those of you who are bird watchers, hypothetically, how do you tell like one of the 10,000 types of birds that look almost identical from one another, right? And similarly, humans, right? How do we tell one human from another? That's a finer grained classification problem than telling a cat from a dog or a human from a cat, right? So face recognition is a finer grained image classification problem. And the reason it works so well, robustly, as of today, is because researchers have spent 20 years trying to solve the face recognition problem because there was always commercial potential there. So that same gusto has not been applied to like fine-grained classification of birds, different types of birds. So a lot of this is also driven by kind of impact, right? It's kind of, researchers will spend their attention where the problems are most impactful.
Do you think that there is a potential issue with the fact that industry has gotten beyond research? I mean, I guess issue is maybe a strong word for it.
No, I mean, however you phrase it, I think it's a great point. It's something we need to be aware of. This is a hard question, right? Like, ultimately, we want to make the biggest contribution to science that we possibly can. And for some people, that answer is to go to industry to make that contribution if you're in computer vision, right? Let me put it generally and then personally. In general, this is a really good thing. It's a good thing to have because it gives people multiple options. You can have students that don't have to just get, like PhD students don't have to just go for a faculty career. They can have an awesome career, academic career in industry and enjoy the perks of industry as it were as well, while having that academic career. So it's a lot of people turn down faculty positions, top tier faculty positions to go and work in a Google or a Facebook or similar. And that's, I think, a really good thing for the field, in my opinion, to have these diverse pathways that people can succeed. Personally, the problems that industry works on are not to my personal taste, strictly speaking. You know, I like to work on problems that are a little bit further out, where the answer is not simply collect more data and then adapt your algorithm. Not to trivialize what industry is doing, but I want to take it away from a performance metric problem where we want to improve the accuracy every year, like a Moore's law kind of scaling, to more like inventing new devices or new types of tasks, like the heart rate estimation or you know, detecting blood pressure from video. I want to study these kind of less common problems today and hopefully scale them in the future.
Oh, I had a certain observation. Wait, am I here?
Yeah, Steve, go ahead.
Yep. Okay. So I think I had a general observation of the problems that are not yet solved. So one thing about them is that basically we've solved the problem of static recognition kind of, but then the dynamic recognition has not really been solved yet, but then that's very important. Would that be kind of like where you're trying to redirect your research towards, like towards these dynamic computer vision, machine learning algorithms? Like kind of looking more like predicting like future and stuff?
I think that, first of all, there's no right or wrong answer to how to classify this. But personally, I think dynamics, maybe the way I explained it, it seems like these are dynamics, but dynamics to me means motion. And you can have real-time object detectors from video or for deformable objects, or you could have image segmentation on the heart where the heart is deforming, right? So you can have dynamics in the traditional problems as well. The additional problems that I've written, they tend to be a little bit, how should I put it? kind of meta. It's hard to say. It's based on your human feeling. It's a lot more human thinking to these problems, right? Segmentation, the fact that I can pose this in such a mechanical framework, means it's fundamentally a mechanical problem, and that's why humans do better than machines, or machines do better than humans for so many of these problems, right?
Oh, because it's very like just collect a bunch of data and then look at very mechanical correlation, right?
Yeah. So these problems, as of today, they're mechanical, right? Take a picture and classify it as cat, dog, or something else. So take a picture and output a binary vector, right? Cat or dog. Object detection, take a picture, draw a bounding box around the object. The bounding box has 4 parameters, a rectangle, right? So it tells you where the center is and the height and the width. Mm-hmm. Segmentation, create a mask matrix that is the same, that is, of, some size in Rn, right? N by N. Instant segmentation, create multiple masks for different object classes. So emotion recognition, how do we characterize emotion, right? How does a machine learn what is sadness in an image? And what is a sad image versus a happy image?
Oh, I see. So going to more like a semantic label on it, that's very, I say, we had to have more context, right?
Yeah, something contextual, I would say. And so that kind of is very interesting. So look, we're approaching 6 o'clock here, so had some good discussion here. Are there any other questions that, any burning questions somebody wants to ask?
Well, I don't know about anyone else, but I have many. But clearly, we don't have time for that. I do just want to personally thank you for coming out and talking to us. It's really been a pleasure. This has been very interesting. Yeah, and hopefully me personally and everyone else here gets the chance to talk to you further.
Awesome. Yeah, likewise, pleasure to be here. And hopefully you guys are okay with the style, a little bit of a different approach to a research talk.
But, I liked it. I thought it was great.
Cool. Hopefully, I highly encourage you to take computer vision courses if you also want to go deeper into this. And hopefully you'll have fun with it. It's a really great field to get into. Okay, thanks everyone. Thanks for having me. Thanks, Ben.
Yeah, thank you.
Thanks, Professor Kadambi.
Great to have you. And yeah.
All right. Bye-bye.